Hello, and thank you for coming to my talk. Thanks also to the organizers for the opportunity to speak. We'll be talking about discrete double fibrations. This work is based in part on a paper by Bob Perret on united theory for double categories. The results of the talk are in a paper called Discrete Double Fibrations that appeared recently in Theory and Applications of Categories. Just to set the stage a bit, let's recall that for any small category, there's an equivalence between presheaves on that category and discrete fibrations over that category. This is induced by an elements construction. And my question was, given that lax functors on a double category valued in spans are presheaves on that double category, and moreover that we have an elements construction for such lax functors, what would be on the other side of a hypothetical equivalence with lax functors on one side? That is, given that lax functors are such presheaves, what's the fibration concept that they correspond to? So on our way toward an answer, let's just first of all recall that a double category is a category object in cat. We'll denote these, for example, by D with D0, D1, external source and target functors, an external composition, which would be given by a tensor, U, an external unit. So D0 is a category that gives the objects and arrows of the double category, and D1 is a category that gives the pro arrows and cells of the double category. So for example, for any Cartesian category, we can form a double category of sets, functions, and spans in that category. For any regular category, we can form a double category of sets and functions and relations as the pro arrows. And finally, there is the double category of profunctors, which is given by ordinary categories, functors, and profunctors. Now, we're interested in lax functors between double categories. These will take objects to objects, arrows to arrows, pro arrows, cells to cells, in such a way as to respect all the internal structure and also the external source and targets. The external unit and external composition, however, are not preserved even up to ISO. Instead, there are certain laxity cells. So for example, on the right in the display, there is going to be given a laxity cell for any pair of composable pro arrows, say M and N, between the composite of the images of these pro arrows and the image of their composite. Now, these will be subject to axioms. For example, a lax functor from a point into span is a small category. The object's functor from categories to sets extends to a lax functor from profunctors to spans. And any representable functor on a double category is in fact lax. For any such lax span valued functor, there is a category of elements construction, turns out to be a double category. So the objects, well, they're pairs consisting of an object of the double category and an element of the set associated to the object by the functor. The arrows are arrows of the double category that have the property that the associated transition function will preserve the chosen elements of the associated sets. The pro arrows are pairs again, consisting of a pro arrow of the double category and a chosen element of the vertex of the span associated to that pro arrow under the functor. The cells are those of D, such that the associated transition span morphism will preserve the chosen vertex element. So this is a double category, and there results a projection double functor to the original double category D. And the lemma is that the two underlying functors are both discrete fibrations. And so this leads to a provisional definition, namely that a discrete double fibration is a double functor, such that the underlying functors are both discrete fibrations. But now noting that a double functor can be viewed as a category object in the arrow category of categories, and also that we're really working in a subcategory of discrete fibrations, a discrete double fibration is equivalently a category object in the category of discrete fibrations. And this is a philosophically appropriate definition and the one that I particularly like. So we'll take cat dfib to be the category of discrete double fibrations. And if we want to fix a particular base, say D, a double category, we'll take dfib of or over D to be the fiber of the resulting or associated codomain projection down to double categories. And so this will give us a category of discrete double fibrations over D. Now, there's an inverse construction for the elements construction. We'll take E sub D to be the fiber of P0 over an object D in the double category. This is a set because the functor P0 is a discrete fibration. Likewise, E sub M is a fiber over a pro arrow, M. And so for the lax functor, we'll take an object to its fiber and a pro arrow to not just its fiber, but the span formed by restricting the source and target functors. An arrow will give you a transition function using the fact that P1 is a discrete fibration. And likewise, using the fact that P1 is a discrete vibration, any cell induces a span morphism that acts as a transition, well, function, but span morphism. Now, this is great. Uniqueness makes all these assignments functorial, but what we really need is the external laxity structure. And so, for example, just with regard to composition, we should be getting, or should be able to find a comparison cell for each pair of composable pro arrows of this form. So recalling that the composition in spans is given by pullback, what we really want is just a function from the pullback of the fibers to the fiber over the composition. And this is given by external composition from the double category E. Now this is great. This gives us a genuine lax functor. And moreover, this is a pseudo inverse for the elements construction in that there's an equivalence of categories between lax span valued functors and discrete double fibrations over D. Now this is great, but it turns out that there is further structure on lax functors. That is, pro arrows of the form are given by certain modules. Just to give an idea of what these are, when you specialize to lax functors from a point, a module between them would be a genuine profunctor. And so we should be thinking that modules are internal profunctors. However, such modules don't compose in general. And so the best we can hope for is to have a virtual structure instead of a genuine double category. And so multicells are given by certain multimodulations. And it turns out, yeah, in fact, lax functors can be made into a virtual double category. Now, the corresponding virtual structure on discrete double fibrations is the following. Let's just recall that monoids in spans and category are the same thing as category objects in that category. But such monoids are also the underlying one category of virtual double category of monoids and modules in spans in that category. And the modules are internal profunctors. So we should be guessing that dfib over D as a virtual double category should be some sort of fiber or slice of monoids and modules in span in dfib. And so we can make this definition. And in fact, the result is that the elements construction and its pseudo inverse each extend to functors of virtual double categories and induce an equivalence between discrete double fibrations over D as a virtual double category and lax span valued functors on D as virtual double category. So that's the main result. Thanks very much for your attention. Happy to answer any questions later on in the discussion sections.